Now these are the types of rejection. There are different kind of rejection based on the shape of the shape and the geometry of the plastic pot. The normal one is the ideal, most ideal one is using stipe pin ejectors. It will be a dia of two dia 3 mm and up to 6 mm. We have the ejectors type pin ejection, and sleeve ejection is kind of very thin slender parts. We are using sleeve ejections, and the blade ejection, if we have very 2 mm wall for the plastic component, the blade ejector will be useful, and the slipper kit will be a ring like a ring kind of hollow shaped parts. We can use it, and valve ejector and air ejection won't prefer much. In India, mostly using on stipe pin sleeve ejection and blade ejection. And these are the before going into the tool design, these are the, we need to select the tonnage for the plastic injection molding. Once we get the part from the customer, we have to calculate the projected area. Projected area is nothing but what are the potting surface or potting surface, what in the potting surface, what kind of, how much area is projected is called as projected area. And the cavity pressure is depends upon different kind of material. For PC, one kind of pressure will be there. For ABS, different pressure will be there. So that we can get from the plastic suppliers. So for calculating force into projected area into cavity pressure divided by 1000, we can get the tonnage. Why we need to calculate the tonnage? Basically, the different plastic pot, the shape of the plastic pot is differ, right? Some pot will be very small in the range of 100 mm. Some pot will be 1000 mm. So we can't mold all the plastic pot in the same machine, right? In order to get the correct tonnage, we need these kind of calculations. Once we get that calculation, we have get the mold base from the different kind of tonnage machines. For it starts from 5 tonnage also is the 5 tonnage. It will be a very toy kind of components. We can mold it in the tonnage, 5 tons. Usually they will call it as baby tons. 5 to 10 tons. There will be kind of very small parts in like nylon gears and all inside the watches and all. You can see the small gears, right? These and all molded in the less than 10 tonnage only. And 35 to 1000 and even 2000 tonnage also will be there for door panels and bumper parts and all. It will be molded in 1000 tonnage machines only. So for getting the correct machines, we need this kind of calculation. For getting this kind of perfect machines, we need this kind of formulas to interpret the to select the correct machines. So now we are talk about now we will see on how to review the pot. Once we get the pot from the customers, we need to view on certain aspects like shrinkage. What is meant by shrinkage? Once we need to apply the scale factor for the plastic component in order to get once the plastic gets cooled, it won't be the same shape of the customer pot. So in order to get the same shape of the pot, we need to apply the scale factor, that is called as shrinkage. Each material having different shrinkage. From nylon to ABS, for nylon it will be 0.6%. For ABS it is 1.2%. So different for the types of, it will be vary. And number of cavities required for the molding the pot. For example, if you want to mold a prototype pots, even the single cavity is enough. If you want to mold 1000 pots and even the lakhs of pots, more number of cavities is good to reduce the mold cost. And the type of gate, as I told you, the gate will be decided based on the production and the quantities required by the customers, and what are the surface demands. What we talk about surface demands, each the plastic part will be the finish will be vary. For some parts, if you see in the if you see in the laptop board, some area it will be rough and some area it will be a very smooth finish. It's all depends on the application, how the plastic is going to be. It's a visible part. These surface demands will be achieving through the mold. There will be sandpaper will be there, oil stones will be there. That kind of things we need to clarify from the customers. And what kind of engraving required? What is draft? Draft. In order to get the plastic ejection, we need the draft. A part with a lesser draft, it won't be a good finish. It will be finishing with it will be a scoring mark will be there. The part with lesser draft. The part with more draft, there are no need of much ejection pressure required. Always design the plastic good draft. It's again the draft depends on the surface finish. If we have the coarse finish, then the draft will be more. If we have the fine finish, the draft will be point. The draft starts from 0.5 to 2 degree for the normal injection plastic parts. If we have the deep drips, then we need the more draft. If we have the smaller drip, then we have the 0.5 degree enough. Always the draft on the coarse side is more than the draft on the always the draft on the cavity side more than the draft on the coarse side. Why? The reason is the cavity, the catching will be happen. The coarse side, there will be a shape. There will be some kind of ejection and all will be there. The shrink during the cooling, the plastic will be get shrinked on the core side only. And what is matching draft? Where the core and cavity is closing, that kind of there we need a 5 to 7 degree required to avoid the rubbing between the metal to metal surface. The potting surface is the second is very important one. If you have the side holes, there will be undercut will be there. To relieve that side holes, we need some kind of side course. It will be on the side of the molding. I will teach you what is side course, and the side course there will be separate kind of calculations will be there. How much the slider has to travel, and there, for actuating the side course, there will be different kind of method will be there. Finger cam method will be there. Hydraulic slider will be there. So that and all I will teach you during the course. For introduction, that only it will take a lot of time. So next I move to sink mark. Sink mark is one of the defect in the injection molding where you can see the depression on the plastic parts, right? The sink mark usually calculated, it's usually formed opposite side of the rib. It will be 0.5 to 0.7% of the wall thickness. When it is more than the 70% of the wall thickness, then the sink mark will come. When it is less than the 50%, then that kind of that time also the sink mark will come. Then the gating point, we need to clarify from the customer where we need to place the gate. Why the gating point is important. If you place the gate point on the top surface, and there will be visible component, right? So always place the gate on the non-aesthetic region. And equal wall thickness and warpage. What is warpage? The deformation from the plastic is called as warpage. And usually the warpage is caused due to the non-uniform wall thickness and improper cooling. So for good plastic part, we need to reduce mainly sink marks, warpage and well lines, and there are so many kind of defects will be there. That's why I am not covering in this session. And what is course? Course and engraving. Course and the length of the hole, usually the 7 times of the dia of the hole. If you go for the split the if the length of the hole inside the plastic pot is more than this criteria, then we need to split the hole. You've seen the hole in the bosses, right? We can split the hole into both sides. And our second thing is we can bigger the dia. Why we need this? If you make the core pins for the mold tools, the pin will be getting heated due to the plastic injection. So once the pin is getting heated, then there will be a deflection on the pin will be there. We won't get the proper shape of the hole inside the components. So in order to achieve the correct holes, in order to achieve the deep holes, we need this kind of, we need to consider this criteria. And engraving, what you can see the plastic parts, these are the 0.4 mm wide, and why this kind of 0.4, 0.25 and 0.2 deep is there. For milling these letters in the CNC, we need this, and we need minimum this, we need to maintain minimum these dimensions. If below or more than this, we can't engrave, because the cutter, based on the cutter, we people are derived this kind of concerns. Now I am showing case study on mold designs. The type of the component is flanged housing, and the type of tool is two-plate tool. And there are different kind of tools are there. Two-plate, three-plate, and hot runner system are there. Now I am teach you on case design on mold design. Two-plate on flanged housing. Of impression is 8 cavity. It is nothing but 8 cavity, and the material is polyacetyl, and the cycle time is 20 seconds. And these are the criteria required to start a mold designer. Before don't know this information, don't start their tool design. So this is the basic criteria we need from the customers. And what are the things we need to look into that before designing? Where the split line will be located. Split line, already I told you what is split line. Where the core and cavity is separated, that is called a split line. Where the slider is touching, there also the split line will be there. And where we need to gate it, what type of gate is required, how we are going to eject it. That means what kind of ejection we are using, whether it is a stipper plate or a straight pin, and how the venting will be required. Venting is nothing but if you close the core and cavity, there will be air entrapment will happening here. Due to this air entrapment, the plastic will get burned once it is ejected. So we need to release the air before getting opened. So for this venting will be there. I will show you how the venting will be. Now, first step is mold split line. For this part, this is the cross sectional of the part. What you see here, A and D won't be the split line. Why? Means if you take the A as the split line, if you take this as the potting surface, then this will be as an undercut for ejecting this part. From ejecting, if you eject from here, and this will be as an undercut. So this is omitted. This we can't able to do it, and this also we can't able to make the potting surface here. We can't able to get from the cavity. From plastic part won't come from the cavity, because this will be an undercut in the cavity side. If you take this and this, so this is the not an option. The only option is B and C, but I am preferring B as the split line. Why I am not choosing the C as the split line is, if you take C as the split line, the more area of the plastic part will be get into the cavity side. Always better to have more area of the plastic part in the core side. The reason is there will be more catching will happening in, always there will be catching happening in the cavity side only. So in order to avoid the catching, we need to take more area of the plastic in the core side. That means B is the better solution for this part. I will clear this kind of, yeah. So B is the perfect potting plane for this part. So I am making the core pin here. I am going to eject the pot from here. So this is the best potting solution for this pot. So next step is, So now I am going to select the gate. For this part, there is a mass protection involved in these spots. So I am going to take a submarine gate. Submarine gate is when we eject the plastic pot, there will be a sharp corners, right? Here, if you see here, there is a sharp corner is there. Due to these sharp corners, the feed system gets separated and the plastic components get separated from the mold. Due to this sharp, there will be a steel or a aluminum. Once we ejected the pot, the feed system and the plastic pot will get separated while ejecting only. So for mass production, this kind of gates is always a most preferable one. So no need of secondary person involved to degating the feed system from the components. So for this pond, there is no much area on the bottom surface. We can't able to eject anywhere on the plastic pot. So this is the best area to eject the plastic pot. So I can't able to use the stripe pin ejectors, because if I am, where is this annotation? So this area, if it is lesser, this area is lesser than 2 mm, I can't able to use the stripe pin method. So sleeve ejection is the best method I can ejection. Sleeve ejection top view, if you see here, there will be like this kind of follow shape will be there, and inside this one I am placing the core pin. Why we need a core pin? Why can't we make a core pin as an integral part of the core side? For example, if you see the core, if you want to make a core pin like this, so there will be a lot of, we need to mill this kind of area, right? There will be a lot of material wastage will be there. So in order to avoid the material wastage, we can place the, we can make this as the core, and this will be taken as separately, we can machining and we can assembling over here. So this is called as core pin. So the purpose of the core pin is to reduce the material wastage, and if there is any deep hole will be there, we can use the core pin. Now, why inserts are required? Why can't we make this part as why can't we make the impression of the core and cavity impression in the core and cavity only? For example, we need this impression in the cavity. Why can't we make it in the cavity or integral only? For example, this is the core and cavity. Why we need these inserts here? The reason is, for example, this is the mass production. For making the mass production, we need a fine finish on the impression. For getting the fine finish, we need to harden the inserts and anodizing. So for getting the fine finish and mass production components, we need the inserts. In order to harden the entire cavity, we can make the inserts alone hardening and easier for the tool makers to get the fine finish. So we can reduce the cost for the for hardening. We need a secondary operation. For that, we can avoid the entire tool need to be hardened. We can make inserts alone, we will harden, and there will be housing will be there inside the core and cavity. We can put the inserts into that. So this is why we need the inserts. So how much L4 is L4? L4 is the amount of plastic inside into the cavity. L2 is based on 2 times of the L4. L3 is the sleeve length, sleeve guiding inside the core inserts. The L1 is 2 times of the L3. The L1, I am talking about the L1 height and the L2 height. And why we need this kind of, this is called as full proofing. We can assemble the inserts in any direction, right?